some lower number of nodes, and each of the control areas knows about its nodes, does not need to so often communicate with the supervisory level, so this cyber cost goes down, but it communicates with its nodes and it communicates with its neighbors. Load distribution control system reduces power losses by providing necessary reactive power at the point of load that results in fast dynamic stabilization of voltage and consequently in an increase of renewable energy that could be delivered to grid. The use of photovoltaic generators and or battery banks connected to inverters that run special control algorithm is proposed to implement the LDCSs. Okay. Now, proposed implementation approach and expected benefits. So, first of all, we propose to the simulation of the distribution system in order to investigate its operation, and to do that, we use the RPM simulator, which was developed at the National Renewable Energy Laboratory, which is properly modified. The simulation results from a model of the wind, solar generation and distribution system can be compared with power quality measurements from the site coupled to measured solar wind inputs. Well, the model will guide number, placement, and set points of local distributed control systems necessary to stabilize the system. Well, one can investigate a bi-level control system with the top-level supervisory controller, where the LDCS can be, this local control system can be programmed to realize grid optimization according to a set of given objectives, such as increased renewable energy penetration, improved efficiency, and improved availability. Photovoltaic generation, the PV generation, is a key technology for realizing the distributed generation concept. Well, how LDCSs can improve the grid operation? Fast local autonomous reactive power control capability to stabilize the PCC voltage to follow a voltage reference set by the top-level supervisory controller. It can also be programmed to slowly adjust the grid voltage profile inside the voltage band, allowing voltage band, and minimize the reactive current flow. Reducing system losses associated with the transmission of reactive power is equivalent to reducing the electricity generation needed during times of peak demand. Actively stabilizing the voltage profile extends the margin to voltage collapse to help prevent grid outages, therefore improving grid uptime. Okay. So the better access of energy from renewable energy sources. Well, momentary active. Sorry, I lost this. Okay, well, too fast. Well, implementation of the LDCS in the RPM sim environment. Now, each control area that consists of certain number of nodes realizing its suboptimal goals generates the settings for LDCSs in each of its nodes. In the RPM sim environment, the LDCS is implemented using inverter module that runs special control algorithm. The inverter is connected to the DC bus supplied by the battery and or the PV array. Well, the voltage command, V reference, from the top level supervisory control gives the set point of the grid voltage at the point of common coupling, PCC, where the voltage feedback signal, VPCC, so the voltage at PCC, is compared with V reference to generate an error signal. Well, this error, this error signal serves as input to the controller, which generates the reactive current IQ inverter injected into the local PCC in order to drive this error to zero. The commands, the proposed LDCS injects or absorbs reactive power in fast response to local control commands to dynamically stabilize the electric grid. The D component of the current, ID inverter, allows for momentary real power insertion and extraction to help for enhanced voltage support. Okay, now, there is still this, I skipped that thing. The suboptimal operation, how this is done. We are exploiting the control capabilities of local power converters at the system level. It increases significantly the requirements on the supporting superstructure. It is proposed of required quality and consumption has to be balanced and the cost of energy has to be minimized. To solve this problem, we propose the suboptimal supervisory control with local distributed control systems placed at local points of common couplings, along with the partition of the distribution system into control areas receiving decision vectors from the system supervisory level. Considering the received control vector, the control system of each control area develops suboptimal control vectors for all nodes in its area. In the paper, the implementation of LDCS in RPM sim environment is proposed. It uses properly modified inverter module of the RPM sim simulator. Well, actually, that's it. Thank you very much.
So, thank you very much, Mr. Bialasiewicz. The questions, please. So, if no, please. No, please.
Hello, thank you for your presentation. I have a doubt about your work, maybe because I didn't understand it quite well. You refer to PCC, the point of common coupling. So you think of this about installing this control on power plants, renewable power plants. Is it right? You propose to control inverters distributed around the distribution network, but they are the inverters who connect renewable sources to grid, or they are like distribution utility tools.
Well,
so
it's implemented using the simulator.
Yes.
Okay? So you have in this have a model of PV.
Okay.
You have a model of the wind turbine, a model of all other possible generators, okay? So you can program it by simply using the mouse and bringing this to the screen, all right? And then, well, everything, all currents, okay, generate and flowing out of the system, okay, meet and the PCC.
Okay. Okay, now I understand. You propose to control the generation from the renewable sources through the inverters.
Yeah.
Okay, and I have one more question. Do you have taken into account to control the response time of every inverter to avoid instabilities?
Well, you can program this, okay? You can program this.
Okay.
Okay?
Okay, thank you.
Right, thank you.
Thank you very much for the questions. Next presentations is from the University of Las Palmas de Gran Canaria, Mr. Gabriel López, please. So that's first, and yes, this one, okay.
Good morning, thank you for coming to my talk today. My name is Gabriel, and as a co-author, I'm going to present a research about the limits of repowering renewable energies in electrical islands. I'm going to divide my presentation into 5 main parts. First of all, a brief introduction about the renewable energies. After that, I'm going to be talking about the objective and the methodology, and finally, the results and the conclusions. Okay, let's start by looking at the situation of renewable energies today. Nowadays, the renewable energies are a general trend in advanced countries to avoid the greenhouse gas emissions and improve the environment. The application of repowering renewable energies involves an increase of the power of the renewable energies in the currently installed units, as well as the implantation of new ones. However, the main problem of repowering renewable energies is its randomness. The renewable energies are only partially predictable, which introduce uncertainty in the control of the electrical system and increase the risk of quality faults. Moreover, there is another important problem related to the electrical islands. The electrical islands are usually small and isolated electrical systems. This supposes a disadvantage to have external sources or sinks to support the quality control of the service and the grid stability. The aim of the research is to discover the quantity of the renewable energies which can be introduced in the electrical system of Gran Canaria. Our analysis is based only in the power time series, avoiding the detailed data, not always available for academic research. So it was necessary a methodology to evaluate the limits of repowering renewable energies in electrical islands based on the analysis of its power time series. The results provided by such methodology will increase the knowledge about the modern electrical systems and which can be useful for planners and public authorities involved in technical and financial decisions about electrical systems, mainly in small islands and archipelagos. The power time series collected don't contain all the information about an electrical system, but contain information about how the electrical system has been adapted to the demand change and to the randomness of the current implantation of renewable energy sources. The power time series used to make the difference analysis include the renewable energies as well as the fossil sources. The renewable energy sources are photovoltaic and wind energy sources, and the fossil sources are the combined cycle and steam, gas, and diesel turbines. In this graphic, we can see in this slide, we can see 2 graphics. In blue color, the demand, and in red color, the power production of the steam turbines. In both cases, during a month. The methodology used to make the research is based on the following steps. The first step is to get the operative limits of the electrical system for the power and the gradient of the fossil sources in the period analyzed. After the first step, it was introduced a multiplicative factor, gamma, which value is bigger than 1 and generate a new value of the renewable energies, going from the current value to a new value. Likewise, the power of the fossil sources change going from the value in the current system to a new unknown value in the repowering system state. The third step is construct the set of numerical constraints to validate the value of the new power distribution and its gradient. After that, they were solved a system of numerical constraints to define if the new solution is feasible or unfeasible. In order to solve the system of numerical constraints, we have used mathematical concepts and computer tools like the convex set theory and linear programming. And finally, the application of the segmentation concept that I'm going to explain after. In order to obtain the operative limits of the electrical system, it's necessary a detailed knowledge about the different power units installed in the system. To define the operative limits, we have used a corrective factor. In case of the power, the corrective factor is 1.2 for the upper values and 0.8 for the lower values. And in case of the gradient, the corrective factor is 1.2 for the positive gradient and the same for the negative gradient. Now, I would like to draw your attention in this point. This data table represents the power limits and the gradient limits of the fossil sources. Pmax and Pmin are the power, maximum and minimum, and the increments are the positive and negative gradients. As we can see, the combined cycle and steam turbines don't have a null minimum power because it's not possible to stop them, and this is one of the main constraints. In this slide, we can see the main equation used. The first one is the equation used in the current system, where the mean of D is the demand, PRNW is the power sum of the renewable energies, and PI is the power sum of the fossil sources. The second one is the equation proposed in this research, where the PI is the new unknown value of the fossil sources power, D is the demand, gamma is a multiplicative factor, and PRNW is the power sum of the renewable energies. Gamma only multiplies the quantity of the renewable energies into the electrical system. Now I'm going to talk about the mean of repowering. The repowering involves an increase of the renewable energies into the electrical system. The renewable energy sources in a repowering system state and in a modified demand state must be priority dispatched into the electrical system. This means that the fossil sources has to replenish this power production depending on the quantity of the renewable energies. The model used to make the research is represented in this equation is based on a global repowering of both renewable energy sources. This model has to satisfy the operative limits, and the operative limits are the power and the gradient. In the future, it will be possible to make a more specific research analyzing the wind energy and the photovoltaic energy independently. For the purpose of finding the gamma values, we have used two main strategies. The first one is a core search, trying to find the feasible and unfeasible limits values. And the second one is a more specific search using this dichotomic search through algorithms. During the research, we could find a big problem. This problem was the high dimension of the equation systems related to the fossil sources constraints. We have proposed like a solution the segmentation of the whole time series in small periods called segments. Every segment begins and ends with a null power of the renewable energy. Regarding to the results, these are 23 segments larger than 4 hours. The renewable energy sources, the renewable energies are more important than the gamma values because they define the power fail. The power fail is the maximum power in every segment of the renewable energies for which don't exist any solution for the constraint equations. In this data table, we can see that the lower values are more correlated with power fail, For example, in the segment 17, for 127.73 megawatts, the system could not be regulated, only modifying the power of the renewable of the fossil sources. One of the results, the segment 5, is represented in this graphic. The blue line represents the demand, and the red line represents the power of the renewable energies. The fault was produced in this point where the demand is decreasing and the power of the renewable energies is increasing. The reason of the fall was that the fossil sources could not reduce their power below to the minimum limit power. Another result, segment 17, is representing this graphic, and the fall was produced in this point where the power of the renewable energies is increasing. And the reason of the fall was the same. The fossil sources could not reduce their power below to the minimum power limit. Finally, the conclusions. This research has been carried out keeping in mind the photovoltaic energy as well as the wind energy. The photovoltaic energy is more correlated with the daily human activity. For this reason, it has less probabilities to produce a power fail. For being the wind energy the main responsible of the faults. Throughout the study, we could detect that the faults are a combination of three factors: the low power demand ignites, the high wind power production of the wind generators, and the low flexible adaptation of the steam turbines and combined cycles. With the aim to avoid these faults, we have proposed some solutions. The first one is the cheapest and is a suboptimal use of the wind generators using a skew-oriented rotor system. The second one is the most expensive and consists in the use of additional sinks and hydroelectric power stations to absorb the power excess in the low demand cases. And the last one, also expensive, is the substitution of the steam turbines to more flexible diesel ones. In the future, another research may be the repowering only of the wind energy. The renewable, the photovoltaic energy sources are more expensive than the wind energy sources. For the reason, in case of a massive introduction of the renewable energies into the electrical system, will be only wind energy. In this case, the equation proposed in this research should be rewriting, analyzing the photovoltaic energy and the wind energy with different factors. And with these conclusions, I conclude my presentation, and thank you for your attention.
Thank you very much for your interesting presentation. Exact on time. We have time for questions, please. So, if it's not the case, I have one question. As I read, understood, you have as criteria defined the part of the wind energy as criterion for the estimation of the percentile part of repowering energies. As I read, understand, is this enough to consider only wind energy for the repowering as a criterion, or we must take into consideration all kinds of renewable energy sources for the determination of the limits? What can you say from what?
I don't understand the question. Could you repeat, please?
The question was about the influence on the wind energy. You have said that wind energy has decisive role for the determination of the limits of repowering energy. Yes. Perhaps it is enough to consider only wind energy for estimation of these limits.
You are asking me about the limits?
Yes, the limits.
There are some constraints of the system, and the constraints are mainly the constraint of the fossil sources. Because, and in order to regarding to the limits about the renewable energies, in the reality there aren't limits, because you can use different systems to regulate the production of these renewable energy sources. We have considered the 100% of the operating of renewable energy. For the reason there are faults.
using these systems to regulate the production.
So the suggestion is, so, okay, so thank you, no question. So thank you very much. So, we have next presentation from the Basque country. Please, Mr. Arrambide.
Okay. Good morning. My name is Arrambide, and I will explain in my presentation with this VSC technology in power system and in offshore wind farms integration. Firstly, I will explain a little introduction of this technology. Secondly, I will explain some application of this technology. And of course, an offshore wind farms integration using VSC converters. Finally, we will explain some commissioned projects and some conclusions about speech. Thirdly, this technology has 5 main ideas. The first one is that reactive and active powers can be independently controlled. This means that each converter can absorb or produce reactive power. The third one is, in my opinion, the most important one, because we want to make a power flow reversal. It's not necessary to change DC polarity voltage. And this is very important for multi-terminal DC grids. This kind of converters have a really low harmonic levels, so sometimes filters are not necessary. This means that VSC substations footprint could be at about 40 or 50% smaller than the previous techniques. Well, the first application of this technology is for bulk power transmission systems, especially in long-distance submarine cables with low losses. Non-synchronized regional grids, as in Europe, is possible with this kind of technology. Of course, a different frequency or voltage rate grids is possible to link, as in Japan or United States. Weak grids and passive grids maybe could be fitted with this kind of converters. As we know, electrical energy demand is growing up dramatically, and the future European supergrid is expected. So nowadays, point-to-point installation projects are, as we can see in the next table, is very interesting Cabrera 4-pole, because it's the first project with hybrid projects with thyristor and IGBTs. It's rated at 500 kilowatts, and it's the first installation with mass impregnated cables. But this technology has, of course, a limit, and the limit is 1 gigawatt of power and 320 kilovolts with cross-link polyethylene cables. In the future, it's expected that these next point-to-point commissioning projects will be done, and deserve to be mentioned the last 3 projects, NorthLink and NSN Link projects, will use mass impregnated paper cables rated at 500 kilovolts. The power is slightly higher with 1.4 gigawatts, and look at the distance, it's more than 600 or 700 kilometers in submarine cables. Ultranet project in Germany, it's a very interesting project because they consider that they can substitute a 3-phase circuit into bipole circuit with these kind of converters. So as I said before, multi-terminal DC grids must fulfill one condition, is that the DC voltage can't change the polarity. So, as we know, the European community wants to make a unique electricity market and super grid. So it's mandatory that VSC converters will fulfill this condition. Nowadays, around the world, only in China, we have 2 different projects of multi-terminal, but they are quite small, with 3 and 5 terminals. It's because for multi-terminal DC grids, we need circuit breakers, and circuit breakers nowadays are limited up to 200 kilovolts. Another milestone was achieved by ABB company in 2005, because they make a special installation, submarine cable to gas platform. They need to feed a high voltage motor to pump gas to onshore. So it's necessary that these variable speed motors could have a different frequency and voltage. So this converter technology can work as a driver, as a motor driver. Another one is back-to-back converters, especially in Japan and United States, because Japan, they have 2 different frequencies. Half of the country is at 50 Hertz, and the other half of the country is with 60 Hertz. So they need to prove this kind of converters as a frequency converter. In the United States, they have 6 different grids, non-synchronized, so they need back-to-back converters. But these kind of converters are really expensive, so developers prefer to use LCC converters and not VSC converters. So let's go to the sea. In the sea, bulk power is expected to be produced by offshore wind farms. So it's clear that offshore wind farms' capacity will be really high, up to 1.2 gigawatt, and deep water will be very big too. So the distance between offshore platform and substation could be more than 200 kilometers. This means that the costs will be really high, and developers start to take into account 2 different aspects. The first one is redundancy of the system, and the second one is maintenance. If we see the overall layout system in this kind of offshore wind farms integration, it's mandatory that more than one offshore wind farm must share a DC transmission system. If we divide this picture in 3 different systems, first of all, turbines. In Germany, nowadays, and for the next years, there are 2 clear tendencies. The first one is that developers don't want slip rings in turbines because maintenance is quite expensive. And the second tendency is that they prefer to use permanent magnet synchronous machine, but at low speed machines, because they don't want gearbox or very fast, high speed parts in turbines. Let's see with United Kingdom. United Kingdom till 2010 year, they didn't use permanent magnet synchronous machine, but nowadays the situation is just the opposite. As in Germany, they don't want to use slip rings in turbines, and they prefer to use low-speed permanent magnet synchronous machines. No gearbox, direct drive. If we analyze the second circuit, it's an integralized circuit, and we have mainly 4 topologies. The first 2 topologies are typical in onshore wind farms, but on the sea, that developers prefer rings topology or mesh grid topology. The last one, it's only applied into offshore wind farms in Germany, in Global Tech and in Dantisk in the North Sea. They want full redundancy in this kind of system. Finally, it has no sense if we connect offshore wind farms in some clusters or in groups for the same direct current transmission system. If a cable fails, it has no sense to lose 3 or 2 offshore wind farms' power. So in Germany, they are considering that for the next year to connect different converter systems in transmission DC grids in the North Sea to achieve a very good redundancy. Here we have commissioned projects. In the left hand, in the left column, we have a DC transmission systems in Germany. Last 2, Darwin 3 and Darwin 3, will be commissioned in the next 2 or 3 years. And in the right hand, we can see different offshore wind farms in which transmission system will be connected as a clusters. As a conclusions, VSC technology will play a key role in development of supergrid and offshore wind farms integration, because offshore business is expected to grow up for the next year. Of course, cables and circuit breakers rate must be bigger, and maintenance and redundancy have a great influence in the design of these offshore wind farms. Thank you very much for your attention. If you have any question, feel free to ask now.
Thank you very much for the interesting presentation. Please, questions? Please.
It's very simple question. Do you mean by VSC, voltage source converter?
What?
VSC in the title. Do you mean voltage source converter or what?
Yeah.
Okay, in that case, did you do any work related to current source converter?
What? I don't understand.
The VSC. It means voltage source converter. It's an inverter, okay? So you have what we call voltage source, and you have what we call current source. CS.
Current source converters means line commutator converters made with thyristors. This is made with...
You are more interested in the voltage level in that case?
No. CSC converters is line commutator converters. They control current.
That's what you call them.
Voltage.
Okay, right. Thank you very much.
There are different contents.
I will discuss with you later.
Okay.
More questions? I have one. You speak about connection of offshore wind farms to the power grid. Usually a standard solution is the use of DC cables, for example. Do you see some options for the use overhead transmission line, HVDC, overhead transmission lines for the transport of energy? Yeah, that's big.
In United Kingdom, they are considering a slightly different concept. They will construct in high voltage alternating current, but in the middle of transmission system, they have to construct a special little platform just to solve the reactive power problem.
Okay.
But the main drawback of this technology is that it's very, very expensive.
Okay. So, thank you. So, next presentation is from University of Las Palmas de Gran Canaria, and presenter introduce by herself, please. Nee, this French, this nice.
Back-to-back converters.
So, back-to-back, okay. Back-to-back, see, I see.
Thank you very much, Mr. Novitskiy. The first thing I have to say is that I'm Eduardo Vega. I am not one of the authors of this work. None of them could assist to this presentation, and I was kindly asked to make this presentation. So probably the keywords here are kindly asked, and well, I do my best. However, excuse me if I have to make use of my cheat sheet to make this presentation. Okay, with this said, the structure of this presentation starts with a brief introduction, analysis of back-to-back converters, analysis of technical and economic barriers for the use of these converters, and I will end with the conclusions. Well, back-to-back converters is the most used type of full power converters which decouple the generator and the mechanical drivetrain from the power grid. All the power generated flows through the power converter, and this converter provides torque and frequency control of the generation. Regarding the converter chasing process, it is required first decide the most suitable topology for the application. The converter control method will depend on it. Constraints definition, such as voltage and frequency of the grid, generator features, etc. The semiconductor selection, taking into account voltages, currents, and their trigger frequency. This is an iterative process, since it is subject of boundary conditions. A simulation is performed, and the performance analysis include thermal study and consumption of the cooling system. The selection of the passive components, the generation, the rectifier and the inverter are decoupled, and there's a DC bus link where it's called the DC link, where a capacitor is installed and it provides some reactive power control and gives some extra power when it's required. Converter simulation to analyze the signal spectra and ensure the coupling of the different stages of the converter. Well, here is a diagram of how this converter works. It's widely used for wind turbine, windmills, farms, and well, on the left side we got the wind turbine with the parts, the blades, the alternator, and the speed power control. In this block, the converter features are summarized. We have all the power electronics in the rectifier and in the inverter, and this is the DC link, the connection between both. We have inductive filters in the connection to the power grid, and there's the pulse width modulator, which controls the response and the power that is given to the network. Analyzing the back-to-back converter, here in the left there is the discontinuous conduction mode signals, which are obtained from a comparison between the reference voltage and the voltage that is received from the rectifier proceeding from the generator. There were between these two signals is processed by a proportional integrator controller, whose output provides the active power reference to the system. Here on the right side, we see the sleep generator output, and the power transmitted to the grid. This is the DC link, and where it's installed the capacitor link, which gives the control feature. This power that crosses this capacitance is the difference between the generated power and the power given to the network. Well, SWOT analysis was performed to analyze which are the strengths, weaknesses, opportunities, and threats of the use of back-to-back converters. And well, regarding strengths, we see that devices based on semiconductors improve efficiency. Capacitors and current filter technologies are very mature to meet the requirements. Pulse width modulator control algorithms are well known and efficient, and all the simulations ensure reliability of real converters. Regarding weaknesses, high power applications require parallel semiconductors and their associated problems. There are new semiconductor encapsulation requirements. Passive components exposed to thermal stress due to switching frequencies. The greater cost for manufacturing, and there are very limited commercial products in terms of specifications. Well, regarding opportunities, all we have heard during these sessions, the renewable market developments need more efficient devices, and as the current technologies are saturating. It's need to improve the overall energy efficiency, both in electrical connections and in electronic systems. And the smart grids and the infrastructure for electric vehicles will boost this market, and more power electronics based on semiconductors will be needed. For last, regarding switches, other types of semiconductors can get better results for lower power applications. It's extended, or now it's extending the use of silicon carbonate semiconductors, not only gallium arsenide or silicon germanate. Well, there are new semiconductors, and it's important to study how we can incorporate them to these applications. The renewable market downtown may affect orders and development of technology. This is a market, and it's need to assess where these converters can be used. Well, the conclusions obtained during this review, the power electronics evolve continually, and it's necessary to integrate new elements and materials that can transform or process energy for end use and to minimize costs. The back-to-back power converters that are currently used in wind power generation systems are widely used, are the most commonly used converters, since they allow full control, bidirectional energy flow, and offer more compact and lighter designs. This type of power converter is the most promising for the sector of renewable energies and future electric vehicles because of its interweighting capacity. This is where new transistors play a key role, allowing operation at higher switching frequencies in high power configurations. The transistors at higher frequencies force the passive elements such as capacitors or coils to be exposed to high thermal stress. The choice of materials and the design is a key factor to ensure the operation and service life of these electronic devices. the emergence of new ferromagnetic materials and new formats capacitors demonstrate that the in current technologies will respond to the needs of the energy sector quickly and in an effective way to all levels of power and frequency for the next generation of semiconductors. It is important to research and develop new and better models of energy storage equipment in the DC bus for a better characterization of the performance of the back-to-back converters. And for last, the future wind turbines will be based on permanent magnet alternators, back-to-back converters consisting of semiconductors control algorithms with pulse width modulator, and will integrate all future progress to be made in power electronics. Well, with this I end my presentation. If you have any question, perhaps I can answer it. If not, there is further information in the paper at the conference proceedings.
Cool. Thank you. So, question, please. So, I have one. Yeah. Question: the back-to-back converters becomes more and more popularity. We have more of these converters. What can you say about the impact of these converters into the power quality in the network and into the network stability?
Well, I think that the tendency, well, this is my opinion, not the
of course,
that the tendency is to distribute all the generation close to every distributed generation will be power electronics, and it will be in a distribution network level, not a transmission level.
Sure.
So the powers we are talking about are not big powers, high bulk power. We're talking about distribution, and perhaps the problem is not with the stability. The problem will come with harmonics.
Sure.
All that
high
power
frequencies.
electronics connected will, and the quality of the electricity. Grid work will have to be done regarding filtering and controlling these harmonics, and I think there will be a problem, not probably with stability.
So, thank you. No question? So, thank you very much.
You're welcome.
The next presentation is from Madrid, Mr. Oscar Monzón-Alejandro. Here. And just a second. So now, yeah.
Thank you very much. I'd like to start my presentation by setting the goal of the work we have done. The main goal is to analyze the role that the energy management in hotels may play in achieving high levels of sustainability on islands. In order to make the presentation, I have divided it into these parts. First of all, there's an introductory background. Then we will analyze the electrical demand in hotels. We will see some means of energy efficiency strategies. We will also see some renewable energy systems that can be installed in hotels. And we will see also the importance of the energy management. We will discuss the relationship between, the possible relationship between the hotels and the smart grids. Also, we will discuss some successful cases, and finally the conclusions. Regarding the introductory background, I have to remember that sustainability comprises three different things. that should doubt together or consider together the environmental issues, the social issues, and the economic issues. Apart from that, islands are highly vulnerable to the effects of the climate change. For example, they are prone to suffer the sea level rises, desertification, water scarcity, and so on. Of course, islands are isolated territories with expensive and weak power systems. The energy is expensive because the transportation cost of the fossil fuels, and they are normally weak power systems because of its isolation. Apart from that, tourism is usually the most important economic sector of islands, accounting for more than 30% of their gross domestic product. Regarding the electrical demand in hotels, we can see in the chart that about half of the total consumption is demanded by the air conditioning system, followed by the lighting systems. As means of energy efficiency measures, we can say that the use of efficient lighting systems is the quickest, cheapest way to improve the efficiency in hotels. Apart from that, of course, we should use efficient equipment and take into account appropriate maintenance, especially predictive maintenance, in order to foresee and see in advance if something is working improperly, in order to change things or upgrade the system. The use of automation systems is also very important to optimize the energy consumption in hotels, for example, by regulating the airflow in air conditioning systems in rooms, or to set occupancy sensors in order to set off all the services in the hotels, in the room of the hotels. Personal and guest involvement is also important. As we will see later, personnel should be integrated in the environmental and sustainability policy in the hotel, and guests are usually naturally involved if they see that the hotel follows certain environmental rules. The use of sustainable architecture techniques is also important by, for example, setting efficient glasses in windows, but also in the designing process of a hotel, setting the orientation, some open space to get natural light or natural air conditioning. Following these measures, can be achieved energy consumptions between 15 and 20% in an easily way, and in some cases even more than 45%. In terms of renewable energy installations, of course, they depend on the local resources where the hotels are located. But for instance, we have geothermal, aerothermal, and solar thermal systems for heating and cooling purposes. We can use the biomass for heating and power production. If biomass is used in a cogeneration system, the efficiency can reach up to 80% or even more. Of course, electrical energy can be obtained by different means of renewable energy, such as wind, high-enthalpy geothermal, solar, and ocean energy systems, as it is the case of the Hawaiian Islands, for instance. The best solution is usually to harmonize a group of different renewable energies to work together in an optimal way. Regarding the energy management, apart from letting the hotel to harmonize the working situation of the different renewable energies and put in practice efficiently the efficient energy measures. Holding a standard is important for hotels for a better position in the tourism market. There are numerous standards that could be served as guidelines to be followed. The most acknowledged international standard for environmental purposes is the 14001, and we have the environmental management audit scheme at the European level. Also, hotels can show their sustainable commitments through issuing sustainability reports, for example, following the Global Reporting Initiative guidelines, which is the most known one. Regarding energy management, the ISO 50001 is the most acknowledged international standard. And here we can see how it should be implemented. First of all, an energy policy should be set by the head of the organization, in this case the hotel, and based on that, an energy planning should be agreed. Then it has to be put in practice and later verified by doing some measurements and monitoring analysis, checking no conformities to see if something should be changed or corrected, and also doing some internal audits. Based on that, there should be a review of the management system, and in continuous process and continuous improvement, the energy policy could be changed if it's necessary. Regarding the relationship between hotels and smart grids, the power systems paradigm is changing from several years ago. It has reached 38% energy efficiency in only 1 year, energy reduction consumption. As conclusions, we can say that hotels can definitely contribute to the energy sustainability on islands. They can collaborate in the most efficient use of the whole grid, also avoiding grid upgrading. However, there is no evidence. The bad news is that there is no evidence of close cooperation between hotels and utilities in islands so far towards a mutual benefit. So this collaboration should be encouraged, although further development in information and communication technologies is necessary, is a must for a stable and secure system operation. Thank you very much for your attention, and if you have any questions, I will be pleased to answer.
Thank you very much for your interesting presentation. Please, questions. So, I have of course questions. Do you have some special recommendation for the hotels in Canary Islands?
Well, regarding Canary Islands, hotels have been implemented several kinds of renewable energies, mostly solar energy, but there are hotels that have geothermal systems based on biomass, and they are good examples to diminish the energy consumption in them. The thing that I have tried to highlight in my presentation, maybe my research, is that apart from that, it's only part of the hotel initiative, is that there should be a collaboration between the system operators and utilities on the islands to collaborate with these huge consumers in order to enhance the renewable energy penetration and the appropriate management on the islands.
Okay. So, thank you. Please.
You presented there a chart with the consumption distribution on the hotels. Can you go back there, please? It's in the beginning, more or less. And you saw that it was around 50% or the distribution of the energy consumption on the hotels. I think it's electrical demand in hotels.
Yes, the chart at the beginning.
Yes. There was about 50% or 48% for air conditioning. Is that for Canarias Island, that chart?
No. It's average hotel regarding it's taking worldwide.
Okay.
Actually, I saw that, for example, in a hotel situated in a cold part of the world, such as, for example, in Gotland, which is an island belonging to Sweden.
Mm-hmm.
It has 50% consumption in air conditioning for providing heat, and in the other part, I didn't remember the place, but it was in the cold climate hotel. This more or less the same percentage, but for obtaining cool.
Okay, I was surprised.
So it's more or less the same, yeah.
I was surprised that could be for an island like Canarias that doesn't need much air conditioning.
The only difference is, for example, for smaller hotels. In smaller hotels, the main consumption is driven by water heating systems, curiously. But it's not curiously, because it's normal, because in big hotels there are reception rooms very big, but it's very costly to get climatized.
Okay. And what you talked about geothermal projects. You mean to get the steam from the earth to in an electrical generator, or
from the earth, yes.
Or a heat exchanger for
not from the soil. The soil through a heat pump. You can produce or install the air cooling system.
Okay.
But it depends, the kind of geothermal system depends on the island. For example, here in Tenerife, it is possible to install high enthalpy systems to produce electricity. But in this island, it has been seen that low temperature systems are, the resource only allows for low temperature systems, up to 40 degrees. Okay. But it depends on the island, the local resources.
Okay. And what about the personal and guest involvement? Do you know some projects or some experience of guest involvement on the?
That's an interesting question, because well, some owners, hotel owners, think that it is necessary to spend a lot of energy to satisfy their guest needs. But it has been proved that by implementing all of these things that I have mentioned, those needs can be satisfied using very low levels of energy. And the implication of guests depends on how they see the policy of the hotel is being implemented. If they see that the hotel follows a sustainable approach to each part of their processes, The guests are naturally involved, become naturally involved in them. Yeah.
So, thank you very much for the questions. So the last presentation for today is from Mr. Langkowski from Germany, please. So, just a second. Yes, so das war Vortrag hier.
Yes, thank you. My name is Hauke Langkowski. I'm from the Helmut Schmidt University in Hamburg, Germany. And yeah, as we've heard today in the third presentation, in Germany we are building a lot of offshore wind parks. At the moment we have around 26,000 wind turbines with a total installed power of more than 41 gigawatts, and also photovoltaic at about a little bit more than 40 gigawatts. Of course, they are not working all the time. At the moment, together with biomass and water, we are having a production amount of about 32 or 33% of renewable energies in Germany at the moment. And the federal government in Germany is planning to increase this percentage up to 80% until the year 2050. And I'm working on a project where we are building a measurement container for the grid impedance directly on the 110 kV high voltage level. The project is funded by the German Ministry for Economics and Energy. Yeah, and the motivation behind this project is that due to the switching operations in the inverters of the renewable energy systems, there are harmonics, and the harmonics can have an influence on the power quality, on the voltage of the grid. And the grid feedback by a renewable energy plant is of course related to the grid impedance at the point of common coupling. We want to measure this grid impedance and detect resonance points so that we can assess the grid feedback better than today, where the grid impedance is just estimated at the moment. We can use the measurement results to optimize the filters and also the control, and solve some issues between the grid authorities and the operators of the renewable energy plants. Harmonics, of course, can have bad effects, lowering the power quality. At the moment, the standards in the certification process, if a renewable energy plant is connected to the grid, is ranging from the 50 Hertz component up to around the 50th harmonic, so up to 2.5 kilohertz. In the near future, these norms will be extended up to 9 kilohertz and then maybe further. So the harmonic influence up to the kilohertz frequency range can be assessed. Harmonics can have more lowering of the efficiency, stress of grid equipment, and can also cause signal damping and failures of other devices if the harmonic levels are higher than the standards at the moment. And if we look at the PCC at the point of common coupling, we can have the grid on the left side if we just assume that there's a voltage source and an impedance, a grid impedance that is of course frequency dependent. We can then assess the current that is coming from, for example, a wind energy converter and is fed into the grid at the PCC. So this is the goal of our project. If we look here on the left side, this is the grid. with an ideal voltage source, and the grid has, of course, inductive elements, for example, transformers, but also capacitive elements from cables, and also some parasitic capacities in the transformer and so on. Ohmic parts, of course, also in the lines and so on. And it is very complicated to model all these effects. So we are trying to measure the grid impedance, and we are doing this by using power electronic, and the power electronic is then turning on a load resistor directly at the PCC with a pulse pattern, so that we get a current form like this. We are measuring the voltages and the currents in this pulse operation, and also during the open loop phase, and the differences between voltages and currents in this simple equation then can be used to get the frequency shape of the grid impedance. And our device is being constructed for the high voltage level, so for the 110 kV voltage level, where we have, of course, a three-phase system with 3 grid impedances. In Germany, the grids are mostly operated with compensated star points, so the neutral line, the Earth, cannot directly be used. We use the simple black box identification of this left side, where these are the unknown impedances, and on the right side, this is our measuring device. You will see on the next slides that we have a power switch. The power switch can be activated in each conductor line separately, and then we have power electronic that is directly working on the 110 kV voltage level. We have a B6 diode bridge, the load resistor, and here an IGBT, of course a series connection of several IGBTs, and this IGBT is then pulsing the load resistor as on the last slide. The power switch is only turned on with 2 conductor lines at a time, so that we can get these 3 linear independent equations that we can then resolve later on to the grid impedances. If we measure the voltages during the pulse operation, we can then say that the voltages are, of course, directly related with the current over the load resistor. And we also measure the voltages during the open loop phase, so before we are pulsing the load resistor. And these are the voltage differences that can be defined. And we can then reformulate the last equations to get at first the loop impedances that you can see here, and then later on the loop impedances can be resolved to the individual conductor line impedances. So also in, for example, asymmetric grid situations, where in each line there may be a different grid impedance, we can determine the grid impedances just by using the voltages and the currents of the open loop and the pulse phase. And this is a 3D model of our measurement container. On the left side you can see the power switch from the company Siemens, and this power switch is connected with the power electronic circuit. So here is the grid connection. The access to the high voltage level is by plugs from cables to the grid authorities. This measurement container will be connected to the grid of Hamburg in the next year. And on the output of the power switch, there is a short cable that you can see here in red, and this cable is going directly to the power electronic. The power electronic is installed within a tank that you can maybe see here on the right side. This tank is filled with an isolation medium. Of course, we are having here very high voltages, 110 kV, so the distances between parts under voltage are very high. We cannot work with an air-insulated setup. In this tank we have the medium ester that is compared to oil that's being used in transformers. Ester is better in environmental aspects. So the whole tank, where there is the B6 diode bridge and also the IGBT and the load resistor here at the back, they are all in ester. And yes, you can see a picture of our current measurement container. We have here, of course, also air conditioning and so on. A very high weight of 26 tons. It's basically, from the dimensions, a normal 40-foot container, where there's a division into an outdoor part here on the left side, where there's a power switch, and an indoor part where there's a power electronic. And yeah, here in this picture there's also already the power switch from the company Siemens. It is a special power switch that does not turn on all three phases at a time. It can turn on each conductor line separately. That is necessary for our measurement method. And the left side here, where there's a power switch, is in the outdoor part of the measurement container, because if we look to the possible short circuit current in Hamburg from the local grid operator, there's a definition of 31.5 kiloamps for a time of 1 second that could occur in the worst case. And due to this high current and relatively long time of 1 second, there is an extreme energy that will go, of course, in case of a short circuit, out of the outlets of this power switch, so that this part cannot be installed in an indoor part as we planned at first, due to the high pressure. And in this equivalent circuit again, so here we have the power switch, and this is the power electronic. As I've said, the power electronic is working directly on the 110 kilovolt high voltage level. So these diodes and also the IGBT are exposed to this high voltage, and we are using several diodes and IGBTs in series. Here you can see a model of one IGBT, one diode stack. This diode stack is consisting of 12 diodes in series, and here in the B6 bridge we have, of course, we are shown here 6 diodes, but each diode is consisting of 6 stacks in series, where each stack is consisting of 12 diodes. So in total in the ester-filled tank there are 432 diodes. And also the IGBT here has to work with the full voltage, and therefore we are using 15 IGBT stacks, where each stack is consisting of 6 IGBTs, so we have 90 IGBTs in series. We are using active clamping if there are voltage peaks, and also metal oxide varistors for the overvoltage protection. And the IGBTs within the tank are controlled over optical fiber cables from a control unit outside the tank. So the conclusion, the reason behind this project is that renewable energies can feed harmonic currents into the grid and reduce the power quality. We want to measure the grid impedance at the PCC in order to assess the grid feedback. So the effect of the harmonic currents on the grid voltages. We want to identify resonance points so that the inverters can be controlled based on the measurement results. So if there's a resonance point, maybe the frequency of the inverter can be shifted a little bit. A special power electronic concept is required for our measurement container, and this should be the outcome of the whole project, to obtain a better filter design to improve the control of the inverters, and also to use it for improved grid expansion or planning. As we've heard before, there are large wind parks planned in the northern part of Germany, in the North and Baltic Sea, and we are having problems with the timetable of the installation of the overhead lines or cables to get this high energy from all the wind turbines from the North Sea down to the south of Germany, where there's more industry and where there are the consumers, and the grid expansion is a little bit behind the timetable. Maybe this can also be used for a better grid planning in the future.
So, for your presentation. Next question. Please.
You are reminding me of my PhD thesis in Japan, implemented work. I just want to know the ratings of the IGBTs and what are the makers. Is it European IGBTs or Japanese IGBTs that you are going to buy or whatever?
The IGBTs are from ABB.
ABB, yes.
We are cooperating with the company Astro in Switzerland.
Yeah. What are the rating, the voltage of the IGBT and the current?
The voltage ratings are 4.5 kilovolts for each IGBT.
And current?
The nominal current is 200 for the setup, but of course the peak current is a lot higher. It's in the kiloamp range.
You don't have okay, I'm just interested maybe in what kind of IGBT you are using. Maybe in internet I can find from ABB.
They are not press pack IGBTs, they are modules, as you can see here in this picture, because of course the Easter can get into the press pack modules. So we have the typical IGBT modules.
Maybe they are made specially for your project,
yes,
in that case, yeah. Or maybe. Okay, thank you.
So, thank you very much for the question. Other, please, during the lunch. Because this, I am close the session just now. Thank you very much again.